Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be looking at modulus transformations. So I should just explain that actually modulus transformations are not quite the same as transformations of modulus functions. So transformations of modulus functions are still really just transformations, right? The sort of transformations that we've seen in year one of A-level maths, but really now they're just happening to sort of modulus functions. Whereas modulus transformations is actually when you start with a function and then the transformed function that you're going to get is in some way, shape, or form going to have the modulus sign. Okay, so the three examples I've actually given here are pretty much describing the full generality of the sort of thing you can possibly come across. But let's try and go through what's on this page systematically. So first of all, I've got to say, in the past, in year one in particular, we've looked at things like this, where f of x goes to a times by f of x plus b, or f of x goes to some number times by x plus some other number, and then you take the function of it. So f of x goes to cx plus d, and you take f of that. Or indeed, you can combine these two to be able to have something that looks a lot more complicated, right? But all these things actually are, these are things called linear transformations, okay? And you can see why they're called linear, because really the process that's happening to this function to be able to get this overall function is linear, and the same thing can be said here. So the process that's happening to this function to get this overall function is linear. The difference here is here you've got the linear part acting on the overall function, whereas here you've got the linear part actually acting on the inside of the function. And obviously in the last case, you've got both the inner part being transformed linearly and the overall outer part being transformed linearly. And of course, by linear, I do just mean something of the form mx plus c, right? I should add, obviously here, a, b, c, and d are basically real numbers. So let's take a look at what I mean by modulus transformations. So modulus transformations are when you start with a function and you end up with a new function, and what you've basically got is you've got linear transformations happening on the inside, but then there is some modulus function hanging around somewhere. Okay, so anything like this is basically a modulus transformation, but of course I've got to emphasize again, all these are in themselves linear. Since we've already basically seen how to carry out very basic modulus transformations, I think we saw that a few videos ago, then I think it's probably best in this video to just go and look at examples to be able to explore how these things are sort of done. And I should also say before I actually jump into examples, which is uh, we're not going to see things of this high level of generality on the A-level syllabus. Even though technically they can ask you something of this level of generality on the A-level syllabus, but my experiences from looking at things in the textbooks and looking at previous exam questions, that really they're going to ask you things on the more sort of basic and lower end of being able to manipulate things like that, or being able to graph things like that. Okay, so we're going to look at sort of the more standard sort of questions that they're going to be able to ask you, and then maybe the very last question we'll look at would something be a bit more challenging. So let's jump in and take a look at the first example. So example one, we're given a cubic, and in fact, the cubic is defined in this case for a particular domain and therefore has a particular range, right? So I could have taken this cubic to just have the entire real numbers as the domain. So I could have had the entire sort of graph here, but because I wanted to emphasize and link ideas from the domain and range part of the functions content we've already done, I thought it would be useful to actually emphasize the fact that we're going to restrict all our transformations to sort of the given domain and range, right? So we are asked to basically work out the sketch of the modulus of f of x, and this is fairly straightforward because we've already seen that actually when you have the modulus of f of x, by the definition of the modulus function, this is going to be the same as the function f of x for whenever f of x is basically non-negative, and it's going to be negative f of x for whenever f of x actually happens to be negative. So we know if I label these branches 1 and 2, we know that 1 tells us that for f of x being positive, the graph of modulus of f of x is actually the same as the graph of f of x. Okay, so branch 2 actually tells me that for f of x actually being negative, the graph of modulus of f of x is actually the same as graph of negative f of x. Okay, so let's now go and plot this. So as you can see, I've already actually marked x values for which the graph of my function is actually above the x-axis, right? So what that guarantees me is the y values here are positive, which means that I'm actually in the first case, so I leave this part completely alone. I do nothing to it at all, which then means I've actually got to do something to this part here because the y values for that are entirely negative. And what am I told? I'm told that actually I have to go and sort of put a negative in front of all the y values, which means that's the same thing as a reflection about the x-axis. So in fact, that point there is basically going to come to some point here. So I'm actually going to get something like that, okay? So if I was to now put all of this together, I'm going to have this red part essentially as being the graph of my modulus of f of x function. So we've been able to graph our modulus of f of x function, and in fact, on an exam question, they might actually get you to figure out these values, right? And you should be able to do that just by sort of using standard ideas of reflecting or stretching or whatever. And of course, I must say, so I only really need to draw the red part for the chunk that I've actually drawn because my domain tells me I only need to worry about x between -3 and 2. Okay, so let's move on to the next question and have a go at that. So example 2, we have the exact same cubic and the exact same domain and the exact same range as we had in example 1. And you'll probably notice that there's going to be a theme in this video with using the same sort of example and then doing lots of interesting things with it. But in this case, the transformation is not just f of x to f of modulus of x, but the transformation is f of x to negative of the f of modulus of x, okay? So the way you would do this is you would start by f of x, and then you would carry out a transformation to get the modulus of f of x, and then you would carry out another transformation to carry out the negative of the modulus of f of x. Okay, so the useful thing is we did this in the previous example. So did this in example 1, so we already know what the graph is going to look like for that. Okay, so let me maybe just put that in and let me do it in green. So we saw that the graph is going to look something like this. I'm terribly sorry for not being able to hold my pen as well as I should maybe, but I hope this is okay. So that's what the first part is going to do. And then the second part is basically going to be quite nice because we know what this is going to do. Let me do it in a different color. Okay, so when we have something where the negative is just being put on the y-axis, so if I have something like this, if I have say g of x going to negative g of x, I know this is the exact same thing as a reflection about the x-axis, right? So that's precisely what we're going to have here. So I'm going to take my green graph and I'm just going to reflect it about my x-axis. So I'm just going to mark points out. So actually I have some level of confidence in that they are going to give me a sensible sort of graph. So I'm going to have something like that. I'm then going to have that point there. And of course, this point here is going to come back to sort of, maybe let me do that. It's going to come back to there. So I'm going to have something that actually looks like something like that. And this thing in red is now the graph of negative of the modulus of f of x, right? And I can even go and mark these points because I know what they're going to be. It's going to be -3, -9, and then the bottom one is going to be -2, -20, and then the 0, 0 is going to remain 0, 0, but this one here is back at sort of the one we've already got there, so 1, 1, -7. Okay, so again, I would say on exam papers, you probably are going to be required to be able to mark these points very specifically. And actually, I should technically finish this sketch because I need to come back here and actually do that. And now this is perfect because this point here is going to be 2, -4. Right, so I hope you see how to be able to get the graph of the modulus of a function with a negative on the outside. And the one last point to say here would be, because we know that the modulus function is going to give us something that's going to be always positive, then when we put a negative in front, we know that this thing here is going to give us something that's going to be always negative, right? And we can see that from our red graph here. The red graph is always sort of below the x-axis in some sense. So let's move on to the next example. Example 3, we have the exact same cubic with the exact same domain that we've actually been working with, but now we're required to sketch this thing here, which is rather interesting. Okay, so again, I'm just going to use the definition of what the modulus function actually says. So I know it's just going to be f of x for x actually being non-negative, and it's going to be f of minus x for x actually being negative. So if I label the two branches 1 and 2, I know that 1 says basically do nothing, right? Because what I have is my modulus, or my f of modulus of x is basically the same thing as f of x. And so it's the second branch that we actually need to pay sort of more attention to, and we know that for the second branch, this is for x being negative, of course. What we're going to have is my modulus, or my f of modulus of x is actually the same thing as my f of negative x, right? But we know what this thing here does. So when we actually put a negative on the inside, this is the same thing as a reflection about the y-axis, right? So we know that from our knowledge, obviously from previous videos, but we also know it from our knowledge from year 1 of A-level. So let's now go and plot these things on the graph. So I've actually marked the x values for which the graph is not going to change at all. Okay, so in all this case here, for my defined domain, for the suitable chunk of my defined domain, I know that all these x values are positive, and the first sort of equation tells me that actually to be able to plot this function, I just leave my initial function alone. So I'm going to completely leave this part alone, which means I only have to worry about the other part. So the part I actually have to worry about is really this part here, right? But now here's where some sort of thinking's got to go into this, which is for all of this part here, the transformation tells me to be able to plot this function here, I've basically got to go to my f of x function, and I've got to now reflect it in the y-axis, right? Because of the negative x being on the inside. So in fact, what I'm actually going to end up with, I am actually going to end up with, if I mark this maybe in sort of red, this sort of region on the positive part being reflected for the negative part. So in particular, what I'm going to have is I'm actually going to have, say, let me mark that point. So say that point there is actually going to get reflected and give me something like this point here, okay? And then in between that, I'm going to have this point here is going to get reflected to give me this point here, which is actually going to be at sort of -1. So it's actually going to be there. And then obviously that point there is just going to remain. So it's going to look something actually like it's going to cross just about there. So it's going to actually look something like this. So I'm going to have that and that. And this is obviously supposed to be smooth and sort of continuous in some sense. So if I, at this stage, go ahead and do the entire graph, so the right side is just not going to change, but it's only going to come up to here, okay? Whereas the left side is actually going to go up all the way to sort of there, because even though that part is not counted on the right side, it has to be counted on the left side because of the way the domain has been defined. Again, another reason as to why I've chosen a domain like this, so you get a better sense of what these things are going to look like. So the graph in red now is my full graph of this function, and I can of course mark my points out explicitly if I so choose, and you probably will have to do this, as I keep saying, in exam papers. Okay, so the point here is going to have the same y value as the point there. The only difference is the x value is going to now become negative because of this reflection effectively. So I hope that's quite clear. Now let's take a look at the next example. So let's take a look at example 4. Unsurprisingly, we've got the exact same function with the same domain, and of course in this case we're now needing to sketch not f of the modulus of x, but f of negative of the modulus of x. Okay, so there are actually multiple ways forward here, and I will actually just talk through two sort of broad ways of doing this. So the first way might be the sort of thing that we've actually already done, right? So we would just go to this thing here and we would just apply the definition of the modulus function. So I know I'm just going to leave my x alone when actually my x is non-negative, and I know that I'm actually going to change my x to negative x when x actually is negative. And of course, we can now simplify this, and we end up with this as our case, and this as the other case. And then we just label this 1 and 2, and we can basically just go and plot each one of these functions separately for these sort of intervals in line with what our domain actually tells us, right? So that's one way of doing it, which is what we did last time, right? But I think a much better way of doing it, so better, is actually as follows. If you actually look back at the last example, what we actually basically showed was when f of x actually goes to f of the modulus of x, then what we showed that this was the same as reflecting the right side to the left. In the previous example, we reflected the right side of the graph actually to the left, right? But obviously, since we have a negative in front here, right, what's going to happen is, so in this case, we've got f of x going to f of negative of the modulus. We're going to basically reflect left side to the right, right? And that shouldn't really come as a surprise, because if we look at this, actually now for our x being less than 0, which in other words, all of this left side, the function f of negative of modulus of x is actually the exact same as f of x. So we effectively do nothing for this entire side, right? And then for the other side, we actually carry out a reflection, which means, so in this case, this statement here makes perfect sense. But the beauty of looking at it like this is that the minute you actually see this, you know what you have to do. You know you keep the left side exactly the same, and you basically reflect the left side to be able to get the right side, right? So let's do a reflection of the left side, and let me change color. So what's going to happen is this point here is actually going to come all the way to the right, and is actually going to come here. So that point there is going to be 220, and this point here is basically going to sort of come across, and it's going to come here, right? It's going to be 3, 9. But of course, because I only want to go up to 2, I don't really care about any of this here. So in fact, I can just not worry about that. And so what's basically going to happen is this point is going to remain the same, and I'm going to end up with something like this, right? So that's what I'm going to get for the restricted domain on the right-hand side. But let me go ahead and just finish off the left-hand side. It's going to be completely unchanged. So that's what I'm going to have. So the graph I actually have now is the graph of f of negative of the modulus of x. And obviously we've been able to mark our points. So I hope you actually found this example quite clear. Let's take a look at the next example. So example 5, we begin with the same cubic that we've been dealing with in all of our examples so far, and of course the same restricted domain and the corresponding range. But the interesting thing in this particular example is for the first time we have to sketch something which actually has two modulus symbols, okay? So at this stage I would say if you've just joined the video, then please go back earlier in the video and see how we've done sort of earlier examples if what I'm about to say doesn't really make a lot of sense. But there are multiple ways forward here. So one way is obviously to be able to use the definition of the modulus function and write this out as branches and then sketch each branch. But that's really not a good way of doing it. It just takes a lot more thinking and a lot more work. The slightly better way of doing it is actually as follows. So we know that when f of x goes to f of the modulus of x, what this actually does for us is, if I actually do it in green, is it says reflect the right side to the left. Okay, so the first step would be to be able to reflect the right part of our graph to actually the left. Okay, And then we carry on and we say, well, we don't actually want just f of the modulus of x, we actually want the modulus of this thing here, right? That's what this thing here is. So we actually continue and we say we need another transformation that's actually going to do this, right? So we're going to have that. And of course, the advantage here now is we know what this actually means because we know when, say, g of x goes to the modulus of g of x, and you can maybe go back and look at some of our earlier examples, this is the same thing really as reflecting the bottom part to the top. So what do I mean by the bottom part? I basically mean something that's below the x-axis, right? So looking at this overall transformation, which is f of x goes to f of the modulus of x and then the modulus of that, as two separate transformations, we can actually get the graph of this from the graph of f of x just by doing the first transformation and then doing the second transformation. So let's do that. So I've done that. I've taken the relevant sort of right-hand side of the graph and I've reflected that into the left-hand side to be able to get this, right? So the sketch isn't perfect, but I hope it at least communicates as to what exactly happens. Now, to finish this off, I've basically got to say the right side doesn't actually change. And of course, the right side is only going to go up to this point here, given how my domain is defined. So that green graph there has actually done the first transformation here, right? And now we're going to do the second transformation, and let me do that in red. And what's that going to do? It's going to reflect everything from the bottom part to the top part, okay? So bottom part to top part. So I can maybe go to a red pen, and I can say that point there is actually going to go up and maybe come up that point there. That point there is going to sort of come up and maybe actually be slightly higher because it should be 7 on both sides and not quite 5, so I'd go slightly higher. So about there, say. And then what I'm going to have is I'm going to have basically something that looks like that. And the same for the second part, okay? This should obviously just be smooth and not quite have a wedge or a kink there. So that's basically the slightly difficult part done, and then everything that was already positive would just remain as being positive. So I'm just going to go over the green part of the graph with just red ink. So the graph I now actually end up with is precisely the graph that I was seeking in the first place. So I hope that was quite straightforward, and I hope you would agree that actually thinking of this like this is actually so much easier as opposed to looking at technical formulas and then reflecting particular branches one at a time. So let's take a look at the next example. Example 6, this should actually remind you of the previous example we've just done, which is we've got the exact same function with the exact same domain, and in fact, even the thing that we actually want to sketch is pretty much exactly the same thing as the thing we sketched last time, but the difference here is now this negative sign on the inside, right? So I'm going to use the same sort of way of thinking as I used last time because it's just so much more efficient. So I'm going to say we want f of x to first be transformed to give me f of the negative of modulus of x. And then once I figured out the graph of this function here, I can then transform that graph to be able to now get the graph of the overall function that I'm actually after. So let's have a think about how we would get the graph of this first chunk here. We know from previous example in this video that when you go from f of x to just having f of modulus of x, so without that negative, that's just basically the same thing as taking the right hand side and reflecting it in the left hand side. But in this case, we go from f of x to actually f of negative the modulus of x, and of course that's nothing other than taking the left-hand side and actually reflecting it in the right-hand side. So let me just write that down. So, okay, so we know now how to do the first transformation, and then the second transformation, well, this is exactly the same as the second part of what we did in the previous example. So we know overall when we've got something like g of x going to the modulus of g of x, then what's actually happening is this is the same thing as reflect the bottom to the top. And of course, as before, by bottom, I just mean anything that actually happens to be below the x-axis, right? So let me now carry out the first transformation, and then we can carry out the second transformation. So I've reflected the key points, right, from the left to the right, and of course the reflection has to be about the y-axis. and any point on the y-axis is not going to change because points that are on the line of reflection don't actually change. So I basically now have to join these points up, but I've got to be careful that this point actually isn't included because the domain that I've been given in the first instance is actually restricted. So I just want the new function to basically have the same domain as my old function. This is going to look something like this. Okay, so even though that's not the best of sketch, I hope it communicates the picture, which is I take whatever's on my left side and I reflect it to get something on my right side. And of course, I only need the relevant chunk, as I said, so I don't have to worry about reflecting that. Let me go ahead and just complete the entire graph of the first thing we've got here, because I, of course, need to count this part here, which is going to be unchanged. So now this green graph that I've actually got, that's basically the graph of the first chunk here, right? So I've been able to do that. Now I'm going to have to basically reflect everything that's below the x-axis to actually being above the x-axis. But see, the great thing here is there's actually nothing to reflect. The green graph is already entirely above the x-axis. So in fact, my red graph actually is going to be just the same, literally the same as my green graph. So I can just maybe do that here. Okay. And so this is basically the same thing as this graph here. There is a remark, which is in particular, you should not be surprised by the fact that the red graph turned out to be the same as the green graph, because it can happen that sometimes you actually end up with a function which is entirely positive, so it never goes below the x-axis. And in that case, if you were to take the modulus of that function to get a new function and you want to graph that, then really, given the definition of the modulus function, that if it's, if the input into the modulus function is actually already positive, you do nothing. So that's basically what's happened here, right? The green curve basically was already positive, so there was nothing we had to do to it. So I hope that's clear. Let's take a look at the next example. So example 7, we have in fact the exact same thing as we had last time, but now with a negative on the outside. Okay, I'm just really sort of including this example for the sake of completeness to give you a good understanding of what happens when all these different combinations of positives and negatives and the modular sign being on the inside or being on the outside actually show up. But obviously, rather than going through the entire argument again, we've seen that argument or variations of that argument now sort of 5 or 6 times. I will just say this is the same as example 6, but the graph is now reflected about the x-axis. So what that would basically do is, if I recall correctly, the graph we actually had last time was something like this. So if I just quickly do that, it was something like that. And what's going to happen now is we're just going to reflect that entirely about the x-axis. So of course we could go and figure out what these points are. That's not that difficult at all. That point there was obviously the origin. This point here is just going to be the x value is going to be -3, but the y value is actually going to be -9. So I can maybe write that in. So it's going to be -3 -9. So the next point is just going to be -2 -20. And the last point is basically going to be the same as the x value for that point, which we know to be 220. So this one actually has to be 2 -20. Okay. Apologies if you felt that was a bit rushed, but as I say, I would encourage you to go back and look at previous examples if you felt that was a bit rushed, and hopefully when you come back to this, you will see that this sort of makes perfect sense. So let's now take a look at the next example. Example 8, we have our beloved cubic that we've now been seeing for all the sort of 7 examples we've seen so far, obviously with the domain restricted, but now we have something looking a little bit different in terms of the sketch of the sort of thing we're after. So how we're going to do this, I'm again going to apply the approach where we start with a function f of x and we transform it to get f of x plus 1, and then we further transform that to get the sort of function that we're actually after, right? So this thing here. So the thing we need to keep in mind is first we have to sketch this transformation, which, we know what it's going to do. So if x goes to x plus 1 on the inside, we know it's a transformation which shifts everything to the left by 1. And then the second transformation is basically the sort of thing we've now seen multiple times, where if we know some function goes to the modulus of that function, then we know that's basically the same thing as reflect bottom to top. Okay, so this should be fairly straightforward. Let's first go and shift the entire sort of function f of x to the left by 1. So what's basically going to happen is this point here is going to come 1 to the left. This point here is basically going to come 1 to the left. This point here is going to come 1 to the left. And so this point here actually is also going to come 1 to the left, right? So I'm going to have something which looks like this, and then like this, and then like this. In fact, I should be careful here because I'm giving this a strange sort of slope, and the slope on this part of the curve is actually very different. So I'm just going to fix that. So I hope you would agree that that looks a lot better. At this stage, I've also got to be careful because my domain is between -3 and 2, and the green graph I've got actually only goes between -3 and 1. So I've actually got to carry on my green graph, and of course what's going to happen is this part here, which was not counted for f of x beforehand because of this domain restriction, now would get shifted and would start to be counted. So in fact, what I'm going to have, so I'm going to have my curve going up to sort of to that point there. Okay, so that's basically the first transformation done. I've now got to do my second transformation, and that's easy peasy because this part here is already positive and that part here is already positive. So the only part that's negative is this part here, and we're just going to reflect that. Okay, so let's do a reflection of that. So we know that point there is -7, so we know we're going to have a +7 when it's reflected. So it's just going to give me something like that, right? So now that's pretty much we're done. Okay, so I'm just going to go ahead and just mark the entire curve in red, as opposed to some part of the curve initially being in green and the other part being in red. So once I've done that, so this is the function we're after, which is f of x plus 1, and we're taking the modulus of the whole thing. Okay. Of course, we could go and work out each one of these points. You should be able to do that actually just from some of the work you've seen in the first year A-level, but I've sort of done that repeatedly for lots of questions already in earlier examples in this video, so I hope that's fine. I'll just leave the details to you to figure out. Question 9 is basically continuing our mission in this video, which is to basically explore different ways of having the modulus sign showing up. And of course, in the previous example, example 8, we actually had +1 on the inside. Now we have +1 on the outside of f, but on the inside of that entire modulus function. Okay, so let's see what the graph of this thing here is going to look like in a sketch. I'm going to apply the same approach, which is I'm going to make lots of transformations such that I end up with sort of this function that we're actually after in the end. So the first transformation is just going to take f of x and we're going to add 1 onto it overall. And then the second transformation is just going to take the modulus of the entire thing, right? So we've now seen these sort of arguments lots of times, so I'm just going to sort of do this slightly quickly. We know that the first transformation is basically a shift of up by 1, so it's this sort of transformation. And then we know the second transformation is actually sort of sort of reflection about the x-axis. Okay, so in fact, it's not just a reflection about the x-axis; it's actually reflect bottom to top, reflect bottom to top. Because the problem with saying that it's a reflection about the x-axis is that would also reflect the top to bottom, but the modulus sign ensures that only the bottom gets reflected to the top and not the top to the bottom. Okay, so anyway, so let's now just quickly see what a sketch of this would actually look like. So you can see I've marked the various key points and I've got them by basically shifting the old key points just up by 1 in each case. Okay, so once I've actually marked these points, I've just got to go and join them up following the same sort of curve as the orange curve that we've actually been given. Okay, so doing that, we get something like this. Again, apologies for sort of not great sketching, but I hope that communicates the message. So we've done now the first part of the transformation. The second part will just require all the negative part to be sent to positive part, right? So it's the bottom part here which is actually negative, and then we just want to reflect that to actually being positive. So I'm just going to go ahead and do that. So this point here is just going to get reflected to some other point there, and we're going to get something like that. And we know from here, because of the work we did, that point there is going to be 1 minus 6. So the point on the top here actually has to be 1, 6. And indeed, we could, if we really, really wanted, go figure out all the other key points that were marked. But I'll leave you to sort of work out the details on that. And what I'll just do is I'll just go over everything which is actually part of the final curve that I'm going to end up with. So all these sort of chunks are going to be part of my function that I'm trying to draw. Here it is. And I hope that example is quite clear as to how we go from starting out with a graph of that for that particular domain to getting the graph of that for, again, that particular domain. And indeed, the red curve is exactly what we were after. Okay, so let's take a look at example 10. So in this case, we of course have the same function with the same domain. But now we actually have this thing here. So you would again notice this. This is very much like the sort of thing we've seen in previous two examples. So in example 8, I believe we had plus 1 on the inside, and then example 9 we had the f of x, but then we had plus 1 on the outside of f, but the inside of the modulus function. But now in example 10, we've actually got the plus 1 on the outside of the modulus function itself, okay? So let's have a think as to how this would be different compared to the last sketch. So in this case, we again have the exact same strategy because I think that this is the sort of easiest way of doing these things. So we're going to work from sort of the inside outwards, okay? So we're going to go from f of x to now just a modulus of f of x. And then once we've got that transformation, then we're going to add 1 to the overall thing, okay? And so we're going to end up with the function that we're actually after. So provided we can sketch this transformation and then we can sketch the second transformation, we know what this thing is going to look like. So we know what that thing is going to behave like in going from what it is, which is this orange curve here, to what this thing here would be. So the first case here, we know what this is. This is the standard sort of thing we've seen repeatedly, which is reflect bottom to top. So the second thing is we've seen for quite some time now, which is when you actually add 1 to the outside of a function, that's exactly the same as shifting the entire thing vertically by 1 unit, right? So let me go ahead and now sketch these things. So the green graph here is obviously the graph of the modulus of f of x, and in fact we saw this in one of the earlier examples, perhaps even example 1 actually, right? So that shouldn't be surprising. And then the second sort of transformation we're going to do is just shift the entire green graph vertically upwards by 1. So let me now do that. To help me do that, I've marked out all the key points shifted up by 1, as you can see, and then all I actually have to do is just basically go over from one red point to another, just making sure I'm sort of parallel to the green curve that I've already got, right? So let me finish that off. Okay, so I hope you feel that this is sort of representative of what I said, and of course we know that this is the graph of the modulus of f of x plus 1, and as before, I'm not going to mark out all the specific points. Do feel free to spend a bit of time to figure them out yourself. You should be able to do that, okay? So let's take a look at the final example, which is actually going to maybe sort of make you think a lot harder about how some of these things can be a lot more complicated. The last example, okay, so this would look rather sort of easy on the face of it, but as you will see, as we start to talk through as to how you work out the answer, you'll see it's actually going to be a lot more work than it might first actually come across to us. So just to introduce the problem, we have the exact same cubic that we've had for the entire video with the exact same domain, and of course then that's the corresponding range. And in the last sort of 3 examples, we've been playing around with having some modular signs and having a plus 1. So we've already seen that initially we had something like, if I just sort of write it on the side here, we had something like f of sort of x plus 1, and then we had modulus of the whole thing. And then after that, we had something like f of x plus 1, and then we had modulus of the whole thing. And then the very last example, we actually had f of x, we had the modulus of that, and then we actually had plus 1. So the slight novelty here is that we've actually got the modulus of x, and then we're adding 1 to it, and then we're evaluating f, okay? And yeah, so let's try and think through this. So there are sort of multiple ways. I'm going to go through the sort of way that we've already been using to be able to answer these questions, but I will try and bring in other ideas when they're necessary. We're going to start just with the definition of modulus of x. And what we actually want to do is we want to be able to write this thing here maybe without the modulus thing on the inside, because that might make life a bit harder for us, okay? So let me maybe make a bit more room and then sort of apply that definition as I've said. So we end up with this. So since that's the definition of mod x, then mod x plus 1 is just going to be that thing there, the entire thing added 1 to, and then when I add 1, I just add 1 to each branch, which basically gives me mod x plus 1 to be the same as x plus 1 for x being non-negative, and negative x plus 1 for x actually being negative, okay? So now when I say f of the modulus of x plus 1, that's the same thing as f of the entire thing here, right? Which is the same thing as taking f of that for x being non-negative and taking f of that for x being negative, right? And when I do that, I end up with these sort of two branches here. And this is basically it, right? So once we've got this, the idea is to go and sketch this branch and to keep it for all positive x and to sketch this branch and to keep it sort of for all negative x, but we've got to also keep in mind that our domain is restricted, so perhaps after we've done the sketch, we can go back and restrict the domain. But let's sort of work through as to how we would sketch that branch there, right? So for x being sort of non-negative, we're just going to have initially start with that curve there and then go to sort of this curve here. But that curve there is basically just that thing there. So it's just going to be that thing there. So we're going to go from f of x to ultimately just f of x plus 1. And this is the sort of thing we were doing in the first year at A-level, and that's really nothing other than just shifting f of x to the left by 1, and that can be written like this. So now let's consider what's going to happen for x actually being negative. So we're actually going to have this. So for x being negative, we're going to have f of x going to this sort of curve here, but obviously that curve there for x being negative is just this part here, which is this thing here, right? And so this, you really should be able to do this from the first year at A-level, but I can imagine that some people are not very comfortable with this sort of thing, so I'll just talk through as to how to sort of know what this transformation is doing. Well, what you want to do is you want to be able to express this in this sort of a form. So the minute you've expressed it in that sort of a form, you know what's actually happening. So you know you're going to work from the inside all the way to the outside. And you see on the inside, you've got an x minus 1. So that's basically the same thing as shifting to the right by 1 unit. So that's what we're going to do first. So after we've done the shift, we know that that negative on the inside is actually the same thing as reflection about some sort of vertical line. But because the negative applies to everything on the inside, the reflection is not going to happen about the y-axis, right? The y-axis would have been the line x equals 0, but because the negative, I would repeat again, is applying to everything on the inside, the reflection's now going to happen about the vertical line x equals 1, okay? So this transformation for the second part of the branch of this function is actually going to be basically you start with f of x, you shift it 1 to the right, and then you reflect it about the vertical line x equals 1, right? So once we've done the first transformation and the second transformation, and we keep the appropriate chunks of our sort of graph that we obtain, we end up with the graph of this overall function, right? So let's now go and do that. I'm not going to sketch these things by hand because they're going to be quite sort of difficult to do. So I've actually done something better. So what we're going to do is we're actually going to make life a bit easier and not worry about the domain restrictions we've been living with all this time. And we're just going to do it for the entire curve, right? Because once we've done it for the entire curve, you could always just go back and say, I just want to keep the curve that I end up with for, you know, between x being sort of minus 3 and 2 or whatever, right? So anyway, so the first thing we've done is basically we've done the shifting to the left by 1. So this is nothing other than f of x going to sort of f of x plus 1. And we know that this is the case for x being non-negative. So we actually end up with this red curve here, okay? And that's clearly, you can clearly see it's been shifted, the orange has been shifted to the left by 1 to be able to get that red curve, right? And then the second thing we actually want to do is we actually want to do this thing here. So we want to go from f of x to f of minus x minus 1. So obviously as part of that, we want to shift to the right by 1. So the orange curve would go to the blue curve. That's just a shifting to the right by 1. But then we must also reflect the blue curve about the line x equals 1. So let's see what that would do. So here we have it. So we've got our blue curve, and then we've got the line x equals 1, and then we've got the reflection actually happening, and we end up with that green curve. Okay, so that green curve is ultimately the final product of what we have for the overall transformation of f of x actually going to f of minus x minus 1, right? So now we know we want to keep that sort of green curve for x being negative, and we want to keep our initial red curve for x actually being positive. Okay, so we end up with this picture here, which is, as I said, our red curve, which is what we wanted for x sort of being positive, so all of this part here where x is positive, and then the green curve for all of this part here for x actually being negative. Okay, so if I get rid of the red curve for x negative and the green curve for x positive, we end up with this picture here. So here we have it. This is basically our final graph that we actually wanted, right? So in other words, we've been able to sketch this function here, and I hope you would agree that it was a lot easier to sketch it the way I actually sketched it with just doing transformations, as opposed to going to this formula and then using the definition of the modulus function repeatedly, doing some calculations, working out points, and so on and so forth, okay? Before bringing this video to an end, it is worth asking a few sort of interesting questions, and one question is actually as follows. So the curve that we actually got from the sort of previous screen, previous page, it actually looked like a quadratic, right? So why on earth is that the case? We started with some cubics, we did some sort of modulus transformations, and then we got something which looked like a quadratic. Okay, well, the answer is the reason why it looks like a quadratic, because if you actually follow through the reasoning I've given, in getting rid of parts of the green graph and the red graph, we actually killed off the second hump. Okay, so because we got rid of the second hump in both those cases, so the cubic that we actually had got reduced to only giving us parts of the cubic, and then when we join those parts together, we end up with something which only actually has one hump in the end, right? But what's even more interesting is if you actually look at the formula, we can expand it out and write it in sort of piecewise function description. We see that when we expand this out, there is no way we're going to actually get quadratics coming out of this. So it is not possible that the graph we ended up with for our initial function is actually a quadratic, even though it looks very much like a quadratic, right? And that's the point I wanted to make, which is in fact, it is not a quadratic, right? In other words, the graph is not a perfect parabola. So it may look like a parabola, it's not a perfect parabola. And let me show you why. So here we have it. So here, the black graph here is actually the graph of the initial function that we actually wanted the sketch of. And then the purple curve here is actually the graph of a quadratic, and this quadratic is not just any quadratic, it's actually a very special quadratic. So what do I mean? So the graph on the left actually is a zoomed in version of the graph on the right. And so if we take a closer look, we see that actually the exact location where that black curve actually crosses the x-axis is the exact same location as where that purple curve crosses the x-axis, and same in that case. And indeed, the same is true for the crossing on the y-axis. So in other words, the purple quadratic has the exact same x and y intercepts as that black curve here. What's even more special is actually the fact that the purple quadratic is the only quadratic which will pass through those 3 points, okay? So just as with straight lines, 2 points fix a line, with quadratics, actually 3 points fix a unique quadratic. So in other words, there is no other quadratic in existence which will pass through those 3 points at the same time. So this purple quadratic has to be the only quadratic which actually would pass through those 3 points. And what we actually then see is because that black curve also passes through those 3 points, that black curve cannot actually be a quadratic, right? And indeed, from that gap there, we see that that black curve is not the same as our quadratic, which basically means the function that we actually ended up with, the transformed thing we were looking for all along, even though it looks like a quadratic, actually isn't really a quadratic. I think that's a good place to basically end this video. Please do hit the like and subscribe buttons if you actually found the content of this video useful. It's a great way for new people to be able to come across the content and also benefit from it. Do say in the comment section as to what you would like to see more videos on. As always, thank you for watching, and we will see you in the next video.